integral over V, okay, volume, that is a triple integral, del dot F, right? So del dot some F vector field dV equal to surface integral. Integral over the full surface, right? So this is a closed volume, means it should have a closed surface. Over this closed surface, F dot F
n
F dot n cap outward normal ds.
Yes.
Okay, so the n is the outward normal. So n is the outward normal. N is the outward normal. To S. So okay, close, which is closed. Okay, so this, if now what I do is I try to put let F, this vector field, you take it as some function, scalar function into gradient of F grad F, where F is a scalar function. Function of xyz. Okay, xyz dot t, if even if it is there, so that's useful. So x is the x bar in Rn R3. Okay, so this is what you take, and if you do it, you just put it into that divergence theorem. So what you get is over V del dot F grad F dV to, so over this S F grad F dot n cap ds. So what is this one? Grad F dot n cap is dou F by dou S, right? So this is over S, F into dou F by dou n into ds. Okay, so this is actually surface area. ds means surface area. So what happens to the left hand side? Left hand side is integral over V del dot F del F dot del F, first one. Okay, so that's going to be del F square, right? Del F dot del F, that is del F square dV plus integral over V. What do you get here? So F into del dot del F, that is del square F dV equal to, so this is the right hand side, you put it, so F into dou F by dou n ds. Okay, so in the place of F, first F, I think let's do this way. So we'll take, let's take it, this is 1. Okay, so instead of taking F grad F, you can also take F grad G also, right? Where F and G are both are, you do that one. I think that is also useful. Okay, so let me write it. So if F equal to add G, where F, G are scalar functions. Then that the same calculation above gives me over V del dot F, right? Del F dot. So instead of this one, what I get is del F dot del G dV plus here over the second term will be F into del dot del G. So there's F into del square G dV equal to here. So integral over S, F will be there as it is. Grad G dot n cap, that is dou G by dou n ds. Okay, so just interchange F and G will give me in the above gives another relation. So what is that relation? So over V del F dot del G dot del F, that is both are same, right? Del G dot del F dV plus over V. So instead of F you have a G del square F dV equal to, here we're just changing this G into dou F by dou n into ds. So this is 1 and this is 2. So 1 minus 2 will give me actually what? 1 minus 2 implies this term, first term, both the equations are same. So what you are having is basically over V F del square G minus G del square F dV equal to, so this is over S F dou G by dou N minus G dou F by dou N. This is your Green's second identity. Okay. This is basically Green's second identity. So first one or 2 is basically Green's first identity. So that's anyway first. So this all these things comes from only your divergence theorem. So now you use the F. Now go back to the first one. So the one that we have here. Okay. So if you look at this one, now you take F being your F equal to phi. Okay. So if F equal to phi, I just leave it there. Okay. So let me write that theorem. Okay. Now come to the potential flows. For potential flows, there is see, basically you are considering a fluid with irrotational flow, inviscid fluid, irrotational fluid. Okay. So then you have a velocity potential for that fluid, for that flow. Now suppose you consider any other flow. So the kinematic energy where any other flow will be always bigger. That's what is the Kelvin's minimum energy theorem. So we'll write it as a statement first. Kelvin's minimum energy theorem. So it just tells you that so let how do you write this one here? So it tells you that basically so kinematic energy, right? So this is minimum kinetic energy. So basically energy means kinetic energy. If half rho u square, right? This is your kinetic energy. Then integral over V, this half of anyway will go, okay, both sides. I'm just writing rho into rho, may be varying also. So this is your U bar square, right? So square means dot product basically. Okay, that is the meaning of mod square. So this is the meaning of square itself. Meaning is that, okay, with modulus u dot u. Okay, so this dv where u is any flow. Okay, so u is the velocity for any flow, any other flow is always bigger than or equal to. So over v corresponding the same corresponding fluid, same fluid kinematic energy for potential flow. So that means rho into what do you have? So grad phi whole square. Instead of u, you have grad phi dot grad phi dv. Okay, so where u is the velocity of any other flow. Okay, any flow for an inviscid fluid. And phi is the velocity potential for an irrotational flow. Irrotational flow. Okay, can you now show? Understand? Do you understand the statement?
Yes, sir.
This statement tells you that, among all the flows you consider, so irrotational flow will have lowest, that is the minimum, okay, minimum kinetic energy. So half mv square u square, right? That's what we are using. So this proof is like we start with the left hand side, okay. I mean, I think we start with something now. Okay, let us see the proof. Proof we'll write. So how am I going to do this is, let's consider both u. Let u is the potential flow, okay. Let's consider v, okay. So v bar is equal to grad phi for potential flow. U is any other flow. And U be any other flow. So once you do that, so you consider this over V. So over V, rho into, you have V bar. V bar is basically potential flow. Okay, this square dV. We start here. So this is equal to, so integral over V rho times. So this we know, V bar is just substitute grad phi mod, grad phi dot grad phi into dV. What is this one? Use this identity that we have right here, right? So this, let me put it as a star, the whatever I tick mark, okay? So tick mark, what happens? Del square phi is 0, right? If del square, that phi is 0 anyway, in that case, okay? So you have a del square phi is 0, and what will happen here? The left hand side is basically, the whole thing is this, so the right hand side you can write it, right? Yes or no?
Yes, sir.
See
Sir,
the
W
second
square
term,
is due to Laplace equation, sir.
yeah, that's due to Laplace equation, yes. So do you take rho constant? The potential flow, incompressible thing is you can always consider rho as constant, or it doesn't matter, just let it be inside, okay? So what will happen here? So this is the left hand side, and since we'll just put it as, since del square phi is 0, so we can see that we can add it, right? This plus integral over V rho del square phi into del square phi rather, okay? That's what you have now, dV. So this is anyway 0, so I'm not getting affected. So this, by that tick mark, whatever that relation that you have, so you can put it here as over S, surface S, rho into phi into dou phi by dou n, right? Dou phi by dou n, isn't it? What is that you have?
Yes, sir.
In that star, in that tick mark. So F, in the place of F dou phi by dou n, phi dou phi by dou n into ds. Okay, so now dou phi by dou n is 0, right? So now what you are doing is you are considering over the volume V, and you have the fluid here, you have some flow here, that is U, and you have a potential flow that is given by grad phi, and you have the boundary. On the boundary, anyway, U, whatever U dot n cap equal to 0 on the solid boundary, okay? Or it is given, it's known, it is given as same, but let us consider the same boundary, no? So whether you have the same boundary is same, so this is same as V bar dot n cap, Okay. So you can put it like the right hand side here, integral over S rho into phi into. So what is this one? This actually tells you that dou. Okay, this is same as dou phi by dou n, isn't it? V dot n cap is dou phi by dou n only. That's what we have. So you put it in the replace and you say that u bar n cap ds. What is u bar? U is basically any other flow, that velocity on the surface. That is that we are replaced, right? So this now what are you going to do? This is what you have, right?
Become 0, sir.
Why is this 0?
U dot n cap.
I'm going to do like I think I'll use this one. So del dot. I think we are going to use what is that Vs? Rho u. Let's put it this way. Okay, so what I'm doing is, let me put it like this: rho phi. It's a scalar into u bar dot n cap ds, right? So this is again, if I use the divergence theorem over V, del dot rho phi u bar dv. Okay, up to here is fine. So this is equal to what? So now what I have is del dot rho phi u bar. So del dot u bar is 0, right?
Yes, sir. U bar is equal to grade phi, del dot grade phi.
So you consider
is
this is an incompressible flow. So maybe del dot, yeah. So if you write it, let me write it. So this is over phi del dot. It is not rho, no. So this simply del rho. Okay, del rho dot phi into u cap u bar. That is one term. Next one, rho into del phi dot u bar. That's another term. Plus, what is the last one? So rho into phi into del dot u. This whole thing into dv. dv, the volume. Okay. So this is equal to. So if you consider rho as constant, yeah, what happens to del dot u? This is 0, right? Incompressibility. Incompressibility gives that del dot u equals any other flow as also you're considering incompressible fluid, right? Incompressibility will give you del dot u equal to 0. So this term is 0. So what happens to this?
This is also 0 because if we consider rho is constant, sir.
If rho is not constant, we know that what incompressibility d rho by dou t is 0, right? So
Yes.
if you consider that one, and you may work with 4 variables. If you work with 4 variables, dou rho by dou t plus, but that is u into what is actually d rho by dt, which is capital D rho by capital, both are same. Total. This derivative is what? Dou rho by dou t plus
Gradient of rho into u vector
gradient
of rho.
u dot gradient rho, right?
Yes, sir.
Gradient rho
E dot u.
dot u. Yeah, this is what you have. So you have this. You already have here. Yeah. Phi into phi comes out anyway. So grad rho dot u cap is basically d rho by dt minus. This is 0, right? This is what we have 0, isn't it?
Yes, sir.
So you put it here as, let me put it as this way. So this is equal to, this will give me phi comes out grad rho dot u cap is equal to minus dou rho by dou t. Dou rho by dou t into dv, isn't it? Plus integral over v. Rho comes out anyway, right? This is the rho Yeah, you keep it is inside. So del phi dot del phi is v, right? So del phi now I replace with v, your potential flow, v dot u dv. Okay. So what is this left hand side? So finally left hand side is basically rho v square. Integral over v rho v bar square, v dot v basically. So this is what finally you get, isn't it? Now d rho by dt. So rho is a function of x, y, t, right? Is this zero? It won't be zero, no? How this first term is zero? If rho is constant, it is anyway zero, right? So usually I think this is true only for maybe that's what. If this is not zero, then you cannot do anything. Okay. So let's see. Okay. So we'll. This is what we achieved. Now simply now look at what is that we do now. So this implies integral over v rho into this is my v minus, yeah, this is like v dot v, right? This is actually v dot v. So this you bring it this side. So this if you bring it this side, so v bar is common, dot product with v bar
V minus U, sir.
huh?
Dot product with V minus U.
V minus u, right? So v bar dot
Yes.
product with v bar minus u bar equal to minus integral over v phi dou phi by dou t, dou rho by dou t. Into dv. Okay, so this is what you have. So now what do you want? What do you want to achieve? So half v square. So I want u square, right? So that you should see that now. Okay, so let me see this one, this quantity. Now you do look at this one. So v times rho into v minus u. This term you try to calculate v minus u bar whole square. Okay, whole square means mod square basically. dv is actually equal to integral over v rho into v square plus, let me write it, so minus 2 into v bar dot u bar plus u bar square. The square means u dot dot. Okay, so u bar dot u bar is basically squares again. So this is your dv. What is this one? This is equal to now use this one. So if you use this one, what do you get? Okay, I think we need to use yeah, v dot u is, now we can use this one, right? This will give me rho v square minus this one, right? Or this term. This term, if you use, what do you get here? Rho v square minus rho v dot u will give me
That one, this
huh?
term, sir. So if we put a rho V square minus
But two is there.
rho one row V dot U is remaining, sir.
Yeah, basically that's what. So if I think we need to consider rho is constant. Okay. Okay, let's do this way. So what I'll try to put this here. So okay, we'll replace. So this is actually the left hand side is this. So you'll have a v rho v dot v, that is v dot square minus rho into v dot u. So you'll have a this is one this thing plus over V, that is your rho u dot square minus V dot u dV, right? So this we can replace, right? So this we can replace. This you can replace now using this one. So this is equal to minus. This is exactly from here now. So this is from star, you can say from star. From star, you can just replace this with the minus sign integral over V dou phi by dou rho by phi dou rho by dou t. Into dV plus here over V rho into u bar square minus V dot u dV. Yeah. Now let me consider rho as constant. If rho is constant, this is 0, right? If rho is constant or incompressible. So what do you call this? Homogeneous incompressible fluid. Then you'll have over V rho into V bar minus U bar whole square dV equal to, this is 0. And what do you get here? So this is over V rho times U bar square. What happens here? So this is U bar square minus V bar dot U bar dV, right? But the thing is that if rho is constant, this itself is 0, right? From star.
Yes, sir.
So here actually we replaced from star. Okay. So star becomes what? Then star becomes, what is star becomes? Rho is constant. First of all, star becomes what? Left hand side is rho V square equal to rho V dot U. Right hand side is 0, right? So integral over V rho U square dV is same as integral over V rho V bar dot U bar dV. So this we can replace. So if I use this, this becomes. So if you use this one, this becomes V times rho bar U bar square minus. Now I can replace this U bar or V bar. That is V bar, right?
Yes, sir. V bar.
This is V bar. I think I need to replace this V. So this if you replace it, so this is going to be V bar square dV. So I think it's only for homogeneous fluid this is true. So now put this. Now what do you do? Now you already have, if rho is constant, then what is that you have? Maybe, yeah, this one. So if you call this becomes what? This is 0. This becomes. So finally I'm writing here, okay, from this if you write, so I'm concluding. So this implies integral over V rho times yeah, this is what you have already done now. So what is that you get here? First of all, rho, you started with rho V square dV is actually equal to rho times integral over V dot U, right? So if this is 0, so basically V dot U dV, rho V dot U dV. Okay, this is what you get. But how do you get this one now? I think we are getting directly now. So from this, now from this, actually, this implies a rho u square. This is anyway positive quantity, right? This is a square. So this is the positive quantity. This itself is done, right? There's nothing to show actually. So this here itself you can put it. So this is always positive quantity because you have square, right? So v bar minus u bar whole square, that is positive. So you have this. From this you can actually see that this is greater than or equal to 0. So v square goes to the left hand side. So this is going to be less than or equal to. So over v rho into u bar square dv. So this is actually half if you add multiply both sides. So that's it. So this is what u is any other flow, right? That's how you start. U is any other flow. So basically it's always bigger. Kinetic energy of any other flow. This is kinetic energy of any flow. Any flow. The left hand side is kinetic energy of irrotational flow. Is this one. Okay. So that's what we have shown. Followed. So what is that we used? So basically we use that quantity. Okay, whatever we have derived, that is your basically your Green's first identity we used. Okay, so we use del square phi. So we got something. So consider rho is constant. I think that is what you need to consider, because we have not considered rho equal to constant. Capital D rho by dou t, if you consider, I think you will get something. You will not get this one. You may not be able to prove. So incompressible homogeneous liquid kind of flow only it's possible for you to have this one. Okay, so a rho is constant, you have this is true. So rho is constant if you take it, so obviously star becomes easily this one. Okay, so you work with directly rho is constant is immediate to see. Okay, and I think this is important. This quantity, whatever we have written now rho is b minus u square. So rho is constant, that is simply will give me this one. Okay, so that exactly will give you what you want. So v dot u is this one, but v dot u is, we actually see this one, right? When rho is constant, this is what you have already seen. V dot u is basically will give me v dot v is same as v dot u. So v dot u we can replace with v square. So that's I think simple. Looks like complicated, but it is straightforward if you work with rho is constant. Okay. Any questions here? Fine, right?
Yes, sir.
Any questions here? Yes. So I think this is this. Yeah. Rishabh, any questions are there?
No, sir. No, sir.
Followed, right? It's all clear.
Yes, sir.
So only thing is that, see, I thought I'll work for dou rho by dou t, capital D rho by capital dt. If I consider such a flow, maybe it is, you may not be able to prove that easily. So if you are considering rho is constant, I think homogeneous fluid is where the rho is constant, the density is constant. You can immediately show that kinetic energy of the irrotational flow is always less than or equal to kinetic energy of any other flow. Okay, that maybe if you equality will come if it is a irrotational flow, same energy will have. Okay, so and the boundary condition is that we have considered a bounded domain where the boundary you have, on the boundary you have the boundary condition is same, satisfied. So boundary condition is satisfied, same boundary condition, obviously, no. So you are not changing the fluid, you are not changing the domain. So you're only changing the flow characteristics basically. So you may have potential flow or you may not have potential flow. So potential flow with the same boundary condition. Obviously, these two are same. Basically, u dot n, either you give right in the, if it is a boundary, it is 0. If it is 0, if it is a solid boundary. If it is some other boundary, you are giving give equal to some known. So that is same known is equal to v dot n cap. So that is dou phi by dou n. So boundary condition is same for both the flows. That is what is, if you consider, you can show that irrotational flow kinetic energy is actually smaller, minimum. That is a minimal thing. Now, what I plan to do is basically we start. I think we have done enough of potential flows. Now we'll go to the viscous equation, viscous flows, viscous fluids, viscous fluid flows, viscous fluid flow equation. So what is that we have? So mass equation is same equations. So what is that? Mass equation is same. Okay. Equation of continuity or mass equation, this is same. So the equation of momentum that we are going to replace, that is your equation of momentum we replace with for viscous flows, that is going to be Navier-Stokes equation. Momentum equation. Third one is energy equation, okay, which we require it in this case. Okay, so energy equation. Conservation of energy, that's the energy equation. These three will give me in principle how to solve the unknowns, number of unknowns, number of equations. So we need to derive only Navier-Stokes equation for viscous flow. Fluid is viscosity. When you're considering the viscosity, so you will have to do that one. Okay, so let me just go through something where I have. So I plan to do this here. Okay, so you remember when you consider the fluid element, you have considered the surface forces are only normal stresses. Remember, for inviscid fluid, you have considered only so now we're going to derive this one. So to see this one, you consider a fluid element. Fluid element means a small thing. Okay, so some small fluid element. What is that you have done for inviscid fluid? For inviscid fluid, only normal stresses are present. What is the meaning of it? You consider this point only perpendicular, that is your normal only. Whatever forces are here, okay, that is basically pressure, given as pressure P in your case, right? So here we are not going to have this one. Okay, let's consider some force that we don't know. So whatever force that you have on this fluid element, you have equivalent. So if you consider n negative thing minus n capital, okay, so we'll have this force. So we're not saying that these actually forces, but we don't know exactly what that force is. So we'll call it simply some force. Okay, so instead of n cap, so that is for incompressible fluid, that is for inviscid fluid. For viscous fluid, so you consider this small this thing, your fluid element you have. So you take a point. So this may have a normal, some normal you have, that is there for every element because it is the geometry, right? So it has an outward normal, and you may have some force vector. So that we don't know, right? So exactly what is that force? For viscous fluids, you may have a what is that? Shear forces, right? So horizontal forces are also there. So you don't know exactly where is the net force acting. So let us look at the net force this way. So if you consider this is your area delta A. Okay, so your delta A is, let us say, the fluid element. So you will have this. Similarly, you will have delta F. Delta F is the force. Okay, so what happens is that if you define this actual finally the stress, what is that you have the stress stress at a point. Okay, this is the point. At a point, let's consider P. P is a point, not P. Let us put something else. What is that? You can shall I put it here? Some other thing. So this is your area delta A element. So let us say at x I have. Okay, point x at x. What is the at x equal to? Now I consider, I assume that the fluid element is so small, and I consider limit this delta A, the area I allow is to go to 0, so that it becomes a point x bar. Okay, so this is actually equal to the limit that and F, that force, the small force acting on this delta A, right? So the force per unit area, force per this area, this is the overall force, not net force. Delta F is the net force. This is the net force on delta A, fluid element delta A. Now, if you consider delta A goes to 0, this is actually the force. This is actually force acting at a point x bar. So this is what we define it as. This is what we call it as stress vector. Okay, this is the stress. It may have horizontal stresses, normal stresses, everything you may have. Okay, so this is basically your stress vector, because force is the vector, right? So this is your stress vector. Okay, so we call it, let's call this sigma. Sigma is a vector. So if you just write it, sigma is basically, sigma is actually, where is this? Sigma at x, and then of course it's moving, the fluid is moving with time t, right? So at particular time t, and it changes with the normal, right? Every time you move x, it is also depending on the normal, isn't it? You see, for this
Yes,
also
sir.
you have a normal. Every time you move this point x in a different times, normal is also changing. So basically your stress tensor depending on not only your position, time, and also the normal vector, unit normal. This is what you have. Okay, now this is exactly what you have is, this is what is your stress. Okay, stress vector. So for inviscid fluid, for what is that fluid? For inviscid fluids or ideal fluids, sigma bar x. Okay, so x bar t n cap. What is this one? Is equal to minus pressure into n cap. You have, no? It depends on n cap. You have something. P is also depending on x, y, z, t, right? So P is actually P of x comma t. So it all depends on there. So in general also you have, it depends on x, t, and n cap. So this is for ideal fluids. Right now you don't know exactly what is this sigma cap. Okay, so you will have basically strict. Okay, so what is the starting point to get this stress? The stress vector, if you want to really see it, it is not actually, it's a matrix, right? Here you have a stress vector here. So what happens here when you consider this? This is what is this sigma cap? Sigma vector is what? Are you following?
Sir, n cap vector, sir, minus rho.
Is it a vector or is it a matrix? It's a vector, right? So yeah, this is a vector. Okay, so stress vector, right? You have. So how am I going to do this? So what is the first step? Next step is what? So you have a fluid element. Okay, so you have a fluid element. At this point, if you are interested, it has a normal. And obviously you also, what information you have? You have a minus n cap here, and obviously here you will have some force, right? Delta A, and you let us say F. I'm not going to write delta A, delta F. So this is a force acting here. So that force only you're calling it as your stress, this thing. So if you see opposite to that, you will have minus F, right? So what is that? F is actually your sigma. So basically, so this tells you, implies, this implies what? This figure tells you that F plus -1 no, equal to 0, isn't it? Opposite forces are 0, no?
Yes, sir.
So where exactly? So this is at minus n cap. It depends on the negative orientation. Inward normal side, if you look at it, that force is minus F, this one. So basically this tells you that the stress, if you consider at the same point, same time, minus n cap, okay, negative is actually equal to minus of sigma cap, sigma bar at this point. These 2 points are same, and here outward normal. Now inward normal, outward normal, when you sum them up, it should be 0, right? This is actually your F, minus F here, minus F here. This is a minus of minus F. This is plus F actually, okay? So this whatever here is actually F. This is already minus F. This is actually minus F because inward force. So both are same, okay? So this is what you can see. So first observation is that this vector, once you change the orientation, inward or outward side, then you will see that is going to be same. Okay, so the negative of that. So if you go inward, obviously you will have that vector change because it's after all a force. Now what is that? Now what you do? So now for viscous flows, what happens is that at this point, not only normal things, it will also have it will also have horizontal stresses, right? Okay, so depending, so if I take, I think the easy way to is n cap equal to I cap I take. Then what is sigma at xt I cap? Will be something, right? It will be something, some force acting along the I, isn't it? That means you take a point and you have a normal, right? So normal is basically, I can write it as nx I cap plus ny j cap plus nz k cap, right? So if my normal is, for example, I direction, what is that force? Force is, it's a vector, right? It's a vector. So I'm representing is like the stresses, okay? These stresses I'm writing in terms of those, okay? So if you we'll see this one. So I'm going to write it in a different notation that is called tau. I'm going to use now, instead of sigma, so I'm going to use tau xx, because you are in the x direction, x component, okay? So first last subscript tau xx is basically, this is your x direction, x component. This is your x component, okay? So this is your I cap. So this vector is I cap, x direction, you will have a tau xx plus that force. Basically it's a force, okay? These are stresses are forces. So you'll have here, what do you have? I want y component that is along the x direction. So that is because I is here. So that is your j cap. Similarly, so tau zx k cap. Do you get this one? So if similarly, if I take n equal to j cap, then the force is basically, force will have So you'll have some force direction. Okay. So in that direction, see, it has all the, because it is a deformation, there is a normal stresses. Okay. Fluid is exerting pressure normally, and also it is simply horizontal stresses, horizontal forces are also there. So that's what you are writing. So now if you look at this one, what I get here is x, y direction, x component, plus force y direction, y component, tau y, plus tau z component along the y direction, that is your k component. Similarly, if n equal to k component, if you take it, here I have to put k, right? So if you put k, similar way, so you'll have tau x component along z direction.
Yes, sir.
That is your first one. Tau y z direction, that is your j component. Tau z component along the z direction, that is your k component. See, these are all something to do. So whatever I'm now underlying, these are basically normal stresses, something to do with normal stresses. So other one is are basically giving the shear. Okay. So yx means along xy direction it moves. Okay. So that's what it means. We will see that one. So now what happens is that so sigma at x n xt t, right, t n cap equal to, so n cap I can write it, right? So I can at n cap. So how do I write my n cap? So this I want to write in terms of this one. So how do I write it? So finally, I need to write this one in terms of these things. So I think, do you have class next class?
Yes, sir. From 21 functional analysis, sir.
Okay. So the the claim, I'm going to put it as a claim here. So next class I will do. So when you write it's a claim, that is what you need to show. Okay. So this is equal to, so eventually I will actually show that this sigma at I. Okay. So x t I. So every time you need not write this xt, I think. So but anyway, so we'll write it. So this into nx. This I am going to put it as nx. This is a already vector with the component nx. Nx is what is basically coefficient of n, right? So that is a scalar. So you will have a n bar at j. I'm not writing xt ny. Similarly, and k. So that means these are the things that I am writing. So in terms of this, you have to multiply with these coefficients ny, nz. Okay. So nx, ny, nz. That is your normal components of normal. Okay, components of your normal vector. If you write it, so that is actually, if you make a product for these things, that will give me, what do you get? Now you try to substitute as though this claim is this is true. Okay, so I'll show you why this is true next class. Now if you put this we already know, no, these three, if you come and put it here, so you will see that finally what is that you get here. So I can put this as a matrix. Can you see it as a matrix?
Yes, sir. Eta xx, eta yx, eta zx. Same.
Yeah, I'm going to write it so simply as a matrix now. Tau xx, tau xx, tau yx, x components I'm putting. Okay, x direction basically, tau zx. That is one. I think we are reversing it, right? So xy.
Correct, correct, sir. Tau xy, second row, tau yy, tau zy,
Yeah,
third row.
we'll see that one. Okay, maybe I don't have time right now.
Yes,
Okay,
sir.
so we'll do that one, and then we'll try to write exactly. So that stresses that basically for viscous fluids, you have all the horizontal forces and vertical forces together. Okay, these we are calling as tau stresses, basically horizontal stresses and normal stresses. Okay, So these tau xx, tau yy, tau zz basically together will give us something that is, we call it a P. Okay, on an average we take it so that we'll see maybe in the next class. Okay, so I'm trying to derive this one. So mathematically also basically this is this required. So this needs to be done. So okay, so maybe next class I'll show you how this is done. This, let me keep it here as a claim. Okay, so up to here no issues, right?
Yes,
Just
yes,
try to
sir.
understand slowly. So if you have doubts, just get it clear so that you understand. That is understanding is required. Otherwise, you may not be able to follow anything. So you finally see some equation which you don't know how you derived it. So try to derive, at least you know what is happening. You should understand how we are deriving here. So earlier for inviscid fluids, only we are assuming that there is only one normal thing. That is normal vector is actually that's what you have, n into p cap. Okay, we have written here. So n into p cap. That is also vector. 3 components are there, no? Those are actually same. Why they are same? Because we see that all directions it is like, the fluid is it's uniform. So uniformly, so I'll give you, that is an assumption for Newtonian fluid. Okay, so that's why all components tau xx, tau yy, tau zz is same. So average when you take that is the same p. Okay,
Yes, sir.
so same p, or actually we didn't take the average. So it's the same p into nx, p into ny, p into nz. So basically tau xx is p, tau yy is p, tau zz is p. So like that we are putting. Okay, so when you finally add it here, you will understand. So suppose all xz, when x z, x y, z x, all these are, let us take 0. What will happen here? Nx coefficient will be, if you add this one, if you add it, tau xx, right? That is your p minus p basically, minus p minus p minus p. So if you add it, so you will see that one. Okay, so you'll see maybe you'll see that one. Okay, so this is a vector
Yes, sir.
as such here. This is a vector. So finally, when you look at the I components will be minus Pn only. Okay. So minus P into Nx, I cap, plus minus P into Ny, J cap, minus P into Nz, K cap. So that is simply minus P into N cap. Okay. So we will see that one slowly. So try to understand every part of it so that you know exactly what is happening. Okay. Go to your class, next class.
Thank you, sir.
Yeah. Bye.